Okay, anyway, so if you go into like the AT&T store and say, hey, give me a SIM card, they won't do it. They'll set, I mean, they will, but they'll set you up on a plan and set them on my plan and charge you a crap ton of money. There are some services that will sell you like a SIM card for like $5 and then charge you like $20 for like 3 months of service, which is all you need for your project by project. So, all right, good afternoon, guys.
Good afternoon.
And friends on the Discord. Okay, as I just said, today is going to be a pretty light day. We're just going to go over a few more sort of interesting sort of properties of Lti Systems. If we have some time, we can talk about the project that's due tonight, and then your next project. And then we'll get out of here on time, and then we'll go for that long weekend. So, are there any questions, comments, or concerns about anything before we start? Don't forget that homework assignment that was supposed to be due 5 minutes ago is due at midnight because I'm stupid and can't label the graph properly. And yeah, so I fixed that because I screwed that up. We pushed the deadline back to midnight. You also have that first Python project that's due tonight at midnight as well. So, and then you'll get another Python. You get not another homework assignment, but another Python project that'll be due a week from Friday. Any questions about any of that? Cool. All right. In that case, let's get through this. So last time we talked about what? We talked about Lti Systems. So today we're going to just sum up some properties. So properties of Lti Systems. Properties. Which we'll kind of list and talk about. We won't really do anything with them, but they'll be important when we move on to actually getting to do some interesting stuff. So properties of Lti Systems. Okay, so the first property, this is going to be just like algebra class, is that the convolution operation is commutative. What does commutative mean?
I don't know, but somebody asked a question.
Ooh, yeah, what's up? Do you want us to name the Python projects similar to the homework? Yes, I would like for you to name the Python project. So yeah, so like last name, first name, Python project, .py. Oh, and I believe I said, someone asked me if you could turn in a Jupyter notebook instead of a Python file. I changed my mind, don't do that. Because I'm sending those off to the grader, and Jupyter notebooks are kind of weird to fire up and do stuff. So just do, even if you did a Jupyter notebook, be sure and like copy and paste your actual code like into a .py file so that we can take a look at it. That way the grader doesn't have to jump through like a bunch of extra hoops to look at your stuff. Cool. All right, I expect I'll probably still get some Jupyter notebooks. Anyway, commutative, what's it mean? What do you mean by both ways?
Like x convoluted, x of n convoluted with h of n, and h of n convoluted with...
Yeah, so it comes with the word commutate, which means to rotate. We can spin the stuff around. And all that means is, and it's got some interesting consequences, right? But that means that h of n, so x of n convoluted or convolved with h of n is equal to h of n convolved with x of n. Which is kind of cool if you think about it, right? That means that if x is your signal, then h of n is the impulse response of the system. But if h of n is your signal, then x of n is the impulse response of your system. They're sort of like pairs of each other, which is pretty cool. That's commutative. So that means there are going to be times when we want to like sort of spin it around and use the impulse response as the signal itself to do some interesting things. So, commutative. today's gonna be just like this. We're gonna basically just sort of list these properties and lightly discuss them and then move on with our lives. All right. In fact, when I was going over it, I realized I probably could have just combined Wednesdays and today's into one class. All right. Next up, the distributive property. Distributive property says that if I take x of n and I convolve it with the sum of two impulse responses or more, right? H of n, h1 of n plus, I almost called it or because I teach 2372 right before this class. So I almost said h of n or h2 of n. We distribute, right? Just like high school algebra class. We can change that into x of n convolved with h1 pi h1 of n plus, not or, h of n convolved with h2 of n. So we can distribute it, right? Now that's got some interesting consequences, right? What is a thing that you could probably do? You guys taken Princom? No? Just no systems?
What is that?
You taken Principles of Communications yet? Cool. All right.
We have to.
What's that?
Technically, I don't think we have to.
No, we don't.
Not anymore?
I think it's
No, that's just
Commutative.
EE.
Oh, it's the E's. Oh, so the E's are in Princom and you guys are here.
Yeah, that's like
Yeah,
the
there we go.
equivalent.
So, anyway, in that case, forget that. Right, another question. I don't know, what's the thing you could do with this, right? That's my question. We can take our signal, we can feed it to two different impulse responses, or feed it to two different systems, and then put them all back together. Can anyone think of an application for that? You guys are taking circuits too, right?
Nope.
Good Lord, what class have you guys taking? Jesus.
One.
Yep. 2 years ago.
The only prerequisite, which can also be done at the same time, is linear systems. Which-
Okay. So you use filters. We don't know anything about filters.
Yeah.
We do know some things about filters. Do we? What class did you talk about filters in? If not,
Linear systems.
oh, you are talking about them in linear systems.
Yeah.
But you haven't talked about them yet, surely.
I took linear systems last
Oh, you did linear systems last semester.
Yeah.
Okay, yeah. So filters, right? So I was hoping somebody had taken Princom and or circuits too, in which case this would have been a lot more obvious. What I was going to get at was we can combine our systems, right? Low pass filter, high pass filter, right? Low pass filter filters out the low frequency. High pass filter filters out the high frequency. But we have like a band pass filter where we want to like do a specific frequency, which is usually like a low pass filter then a high pass filter next to each other. All I was going to get at was this property lets us do interesting things like create band pass filters, where h of 1 is the impulse response that gives us a low pass filter, and h of 2 is the impulse response that gives us a high pass filter. You can smash them together and get band pass filters. That's all I was getting at, but I misunderstood the prerequisites for this class. Does that kind of make sense? All right. Next up, the associative property. This one just says that if we have, let's say, the output of our system is equal to x of n convolved with h1 of n convolved with h2 of n would be the same thing as taking x of n and convolving it with h1 of n convolved with h2 of n, right? This is that we can take two impulse responses and sort of convolve them together and use that as our new impulse response and feed our input signal to that. Does that kind of make sense? Cool. All right. So those are our three important properties. One, that it's commutative, we can spin stuff around. That we can distribute, which means we can sort of combine the responses from different convolutions together. And the associative property, we can sort of, the order in which we do things doesn't necessarily matter. We can combine these things together. Any questions about that? Cool. All right. The associative property. The next thing that I want to talk about is representing these systems graphically. Like a lot of things, it's useful to kind of block diagram everything out. So representing systems graphically. Or I'm just going to put in here block diagrams. All right, we're going to start using this notation where we'll have an input signal, x of n, and it might do some stuff like this. It splits off, and then we'll have a box, and we'll say that box has h1 of n. What is the output of that box going to be? Any guesses?
Is it the two convoluted?
Yeah, it's too convoluted. That's all I was looking for. So the output of that box is going to be x of n. What's that?
I saw a blue ring right there.
X of n convolved with h1 of n. And then maybe we'll have a second leg. And this box has h2 of n. And the output of that's going to be what?
X of n.
Just checking. X of n convolved with h2 of n. And then we might bring them back together. Using a little circle with plus sign in it. But we can guess what that does. Means our output y of n is going to be equal to x of n convolved with y of n, not y of n, man it's Friday, okay, convolved with h1 of n plus x of n convolved with h2 of n. Okay. So that's what we're going to start to do. We're going to start to like represent these operations as block diagrams. You know, and it's not even too hard to see how this is going to go into code, right? You know, I've got x of n. I've got a function that's going to, I'm going to convolve that with h of 1. I'm going to convolve that with h of 2, and then I'm adding them up together, right? So the block diagram gives us a sort of, I think, an easier way to kind of look at it and simply see, oh, this is what we're doing, instead of looking at all a bunch of, you know, mathematical derivations. Cool. So using what we just talked about, is there a way to simplify this block diagram?
Could you just put h1 of m plus h2 of m in the same box?
You bet, yeah. So we could simplify this. Still got x of n, right? Because we talked about that distributive property. We just have one box where we added h1 of n and h2 of n, and we quite literally mean adding them together. to get our response. Y of n, which is equal to, bless you, x of n convolved with h1 of n plus h2 of n. And as we just talked about, these guys are equivalent with each other. So we can refactor just a little bit. Cool. Any questions about this one? Pretty straightforward. All right. Let's do one more of these. All right. If I say, do it this way. H1 of n, that feeds directly in H2 of n. And I have y of n on the outside. My question for you guys, what is y of n equal to?
X of n convoluted with h1 of n convoluted with h2 of n.
What's that?
All of them just convolute with each other.
Yeah, right. So x of n convolved with h1 of n convolved with h2 of n. And like before, is there a way to simplify this block diagram? You all right, man?
Choked spit.
People in Discord are getting answers.
What's that?
People in Discord are getting answers.
Oh, what do they say?
Right.
Convolve the h's first, and then convolve x with that. You're absolutely right. Convert one block, which is the convolution of both impulse responses. You're totally correct, right? So what I was looking for is this, x of n. We could have one function, one block, that's h1 of n convolved with h2 of n. And that gets us y of n, which is equal to x of n convolved with h1 of n convolved with h2 of n. And there are all kinds of reasons for why we would want to simplify that stuff. Okay, so any questions about those block diagrams? Obviously they'll get more sophisticated as we move along, but that's the gist. Cool, all right. So let's make this our next little section here. We'll say that Lti systems adhere to the same rules of stability and causality. All right, let's talk about what that means. First up, stability. What was stability? What makes a stable system?
When it's bounded.
What's that?
When it's bounded. When it's not going infinity.
Well, there's more to it than that. Give you a little more, I don't know, rigorous in your answer? A little more formal?
If a bounded input, you want bounded output.
I mean, bounded input gets you bounded output. Give it something finite, you're going to get something finite back. So for LTI systems, in our impulse responses, it's going to be basically that. What we're going to say is this, that there's some bound h, which is equal to the sum of k equals negative infinity to positive infinity of the absolute value of our impulse response, and that needs to be not less than or equal to less than positive infinity. Cool. So is, let me call this an example, if is an impulse response that's just the impulse stable? Cole Roper on Discord says yes. Why? So does Curtis. You guys could talk instead of typing stuff. We would be able to hear you, I think. So he said it has a value of 1. Every value of x returns either 0 or 1. Cole says bounded input, bounded output for every value of x besides x0, the function will be 0. Not quite. Because we're talking about, when we talk about b of h, we literally mean the sum of the expression. So remember, our impulse response is at 0, 1, 2, -1, -2, right? It's 0, 0, 1, 0, 0. So I guess maybe a better way to ask this question is, what is b of h equal to? Yeah, this guy say 1, right? Because it's just, 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 0 plus 0 all the way out from negative infinity to positive infinity. So in this case, b of h is equal to 1. Let's do another one. What is our impulse response? What if it's equal to the unit step sequence? U of n is h of n equals u of n stable. You see u of n used a lot in as the impulse response. Is it stable? Edward says not stable. How come? Curtis says he thinks it's stable. What you guys? You guys are being all quiet. They're super chatty over here.
I think not.
Why not?
Because even though it's only positive after 0, you're still positive for infinity. Or
Yeah,
1.
because again, it's not about the inputs, it's about the sum, right? Our definition here, b of h is equal to the sum of the absolute magnitude of h of k all the way to infinity, right? So for u of n, we sort of do a lame job of drawing. Well, 0, 0, and then 0 goes to 1, and then it's 1, 1, 1. It stays that way forever. So what is b of h equal to? Yeah, it's equal to infinity, right? Because we're going to add 1 plus 1 plus 1 plus 1 plus 1 forever. So b of h is equal to infinity. Therefore, h of n equals u of n is not stable. Curtis asks, so how is it a bounded input? And it's because we're actually not interested in inputs, right? When we talked about the systems themselves, we said bounded input gets you bounded output. But remember, we're using a different definition. We're only talking about the stability of the impulse response. And that's governed by this equation right here, which says we add up all of the values of the impulse response. And if it's finite, then it's stable. And if it's infinite, it's unstable or not stable. So when we're discussing the impulse response, it's not about the value of the input. Cool. Okay. He's typing. Seriously, you guys really ought to just talk. This would save us a lot of time. You're welcome. All right. So what are we doing? What are we saying? Okay. Next up is causality. What does causality mean, or what did it mean to us before?
It only depends on values up to the value you're selecting. It doesn't depend on future values.
Right, it doesn't depend on future values. So what do we think that means about the causality of our impulse responses? How do we design our impulse response to ensure that our LTI system is causal?
We don't shift it forward.
What's that?
We don't shift it forward.
We don't shift it. Yes. What's another way to say that? I guess. I think you're absolutely right. But you said it in a kind of weird way. There we go. I'll just give it to you. H of n is equal to 0 if n is less than 0, right? Means when you're designing your impulse response, you can't put anything before 0. Nothing. Your impulse response can't have anything that happens in the future. Does that make sense? So we can only start at 0 and go afterwards. So we could have, you know, an impulse response that looks like, you know, that, if that's 0, but we can't have that. That's not allowed, right? When you're designing the impulse response, your impulse response sequence has to start at 0. It can start after 0 if you want to do some weird delay stuff, but it can't happen before 0. This will be strangely important when you do your project next week. Okay. Let's see. Two more things to talk about. So any questions about stability and causality for our impulse responses? Basically all that boils down to just two things. It's got to be stable, which means that or it doesn't have to be stable, but to be stable, the sum of the entire sequence of your impulse response sequence has to be finite, such as, you know, the impulse sequence itself is stable, but the step sequence is unstable because it adds 1 forever. And causal. When you're creating your impulse response sequences, you can't have anything that starts before 0. Everybody good? Cool. All right. So this one is kind of a silly formality, but we're going to talk about it anyway. I'm going to call this defining the impulse. Impulse. Response. And it's pretty simple. Remember, what was it, a couple days ago? We talked about that ideal delay system. Or where we said that y of n is equal to x of n minus nd, right? But now we're defining everything in terms of our impulse responses. So if that was our original definition of the system, we now need to have a new definition that says that y of n is equal to x of n convolved with h of n. So what I really care about is what is h of n equal to? How do we redefine our system to now be in terms of the impulse response? I'll give you a hint. The answer is very, very simple. I'll give you a hint. A second hint. It's in the name, the impulse response. Now I see everybody's trying not to make eye contact with me. Somebody wager a guess.
Would it be x of n convoluted with y then?
What's that?
Would it be x of n convoluted with y then?
X have been convoluted with y, then no. It's a good guess though. We're changing the definition, all right? But it's got to be based on that guy still, right? Cole also said X-Men convolved, like the inverse of X-Men convolved with y of it. No, that's way too sophisticated. It's much simpler than that.
Well, if we're talking about the top one, do we like this? Can we do x of n minus x of nd and then move it over across the?
Here's the third hint. So it's not so we already have x of n in our definition, right? Which means our h of n is no longer has anything to do with x.
Delta.
What's that?
Something to do with delta.
Yeah, it is something to do with delta. Yeah, you're absolutely right. See, the problem is now I've like committed to this sort of Socratic thing where I'm like waiting for you guys to give me the answer. If I just give it to you now, then I'm just doomed for the rest of the semester, right? So let's do with delta, yeah?
ND. Delta ND.
What's that?
Not delta N, but delta ND.
You're so close, man. So just type it. Yeah, there we go. Basically, here's the punchline. You just take what we were doing before and replace all the x's with deltas. So h of n is equal to delta n minus nd. Yeah. So what we defined before as our thing that happened to x now just happens to the delta function. So, for example, if I asked you to write a Python script to do this ideal delay system, well, then first you would have your convolution function that you're creating next week, and then you would just convolve it with a delta sequence that was shipped over by some amount, right? So we're always going to use delta. We're going to use delta sequences and just kind of push them around a little bit, just to make sure we've driven that point home there. If we wanted a moving average, otherwise known as a low-pass filter, then we might do something like this. Before, we would define it as this: y of n equals 1 over some values m1, m2, which is sort of the window that we're using, plus 1 times the sum, k equals negative m1 to m2 of x of n minus k. So now, what is our h of n?
The same thing, but instead of x delta.
The same thing, but instead of x delta. You're absolutely right. Now, let me finish writing this, and then hopefully we can talk about why we care. Y, so to m2, now it's delta of n minus k. You guys are all computer engineers. Why would we care to make the distinction between these two? Right? We already have a definition for y as a function of the output signal as a function of the input signal. Why do we care to redefine it in terms of the impulse function? Why is it worth our time? Why can we spend 45 minutes talking about it?
Because we're going to use it so much.
Well, it's not that we're going to use it so much, but think about it in, hold on, never mind. In terms of computation, right? Look at the original function, right? If we want to calculate y of n, we have to do what? We have to come up with this constant, 1 over n plus 1, m1 plus m2 plus 1, and then do this like addition thing over and over again continuously forever until we get our result, right? It's a lot of math. Instead, what are we going to do? To do the exact same thing, we're going to calculate h of n one time, right? And have our h of n, store it in memory, keep it forever. And then all we have to do now is take x of n, slap it with h of n to get our answer, right? It drastically reduces the amount of computation that you have to do, right? Whereas the first paradigm requires you to be continuously doing all this math, right? And it doesn't seem like that much math for something that's really simple, like this moving average thing, but we're going to do some sophisticated stuff. And to do that sophisticated stuff, it requires tons and tons and tons of computations. Whereas instead, all we have to do is calculate our impulse response, get that one array that has our impulse response, and then just hit it with convolution, and we're done. Like I said, it drastically reduces the computational load of what we want to accomplish. Ooh. There's my idea for your project for the week after next. We'll have like one, this might be pretty cool, I'm gonna look into this. So like we might do one, the same operation, right? The same sort of system, do the first paradigm, and then do it with the impulse response, and let's compare like how long it takes to do both of them. Maybe we'll see that the impulse response one is like dramatically simpler or faster. So we might not be quite there yet. All right, questions about that? All right, we convert everything to impulse response so that we can calculate that guy just once and convolve it, right? Way reduces our computational overhead. Okay. All right, one last thing before we call it a day is let's go back to stability really fast. Back. Because there's a little bit of terminology that we're going to take with us that you've probably heard of before. Remember, stability says that B of H must be equal to negative infinity plus infinity, the absolute value of H of n. It's my little alarm that says, hey, shut up, class is over. but I'm not quite done yet. Okay, that's our B of H. Now, we talked about things can be stable or not stable, right? Our impulse response can be stable or not stable based on what this is. Now, there are times to use both, right? You've seen in your linear systems class maybe that you can use the step function as an impulse response to do interesting things. And so the last little bit of terminology that we're going to leave ourselves with is this. There are basically two paradigms that we're going to bounce back and forth. If B of H is less than positive infinity, i.e. is it bounded, then the system is referred to as a finite impulse response, or FIR system. And likewise, if B of H is equal to positive infinity, then the system is an infinite impulse response, or IIR system. Cool. So you've ever heard that before? FIR, IIR, that's what we mean. The stability or instability of that impulse response. And there are reasons to use one over the other depending on the circumstances. So real quick, as an example, H of n equals delta n, FIR or IIR. Good, FIR, finite. So we already discussed it was stable. What about H of n equals U of n, FIR or IIR? Good, IIR. What about H of n equals all these ones we talked about before, log base 10 of n, FIR or IIR?
IR,
Why?
whenever it's 0.
Yeah, right, because it's got that zero negative infinity business hanging out there, right? So yeah, so that's IR. What about H of n equals the absolute value of alpha n? Is it FIR or IIR?
FIR.
Always? Someone's typing it. Two people are typing it. Ooh, controversy. FIR. IIR. Depends on the value of alpha. How does it depend on the value of alpha? Ooh, Edward, you took that to a dark place. Okay. Alpha greater than 1, yeah. So for alpha, let's see, an absolute value of alpha that's less than 1, it's going to be FIR, right? Because that is going to exponentially decay. But if alpha is greater than or equal to 1, then it's IIR, right? So it can depend on the constants that we throw at it as well. All right, any questions about that? Cool. Well, thank you for sitting through that. Like I said, I know that was kind of dry. We didn't really do anything interesting. We just kind of listed out some definitions. but these things will all be important and useful to us down the road. Are there any questions about, so your Python project is due tonight at midnight. You've just now at 12:30 it released your next Python project where you're going to have to implement convolution in Python. We already talked about that this was going to be the thing. It's a lot of fun. I really enjoyed it. I did it yesterday when I was sort of preparing the assignment. I thought it was a lot of fun. The catch is you are not allowed to use any external libraries. I want you to implement the convolution like straight up, right? NumPy has a convolution function. Don't use it. You have to take the lists, take the x of n, take the h of n, give me the y of n based on the thing. I included some helper functions in the description. One I called stem, which is it just draws the lines. It creates the collection of lines that you can use to connect the horizontal axis to the vertical axis. You don't have to use that if you don't want to. Most of you should already have that from doing the first project. But I wrapped it up into one function. I also did a thing called trim, which you will explore and see why it's important to your solution when you do the project. But I'm not going to spoil it because that would sort of defeat some learning process. Like I said, it was a fun project. I enjoyed that project a lot when I did it yesterday. I think you're going to enjoy it. And it's going to teach you a lot about how convolution works. And then you'll have a function convolution that you can use to do more interesting things. Let's see, some folks have questions. For the project, you want certain requirements for the inputs, so long as, let me see, 2 inputs, showing 2 signals on the graph, your convolution, are we good? Yes. So you just need to, I gave you a starter function that has like the empty shell of the convolution function and then like my own little test case. You don't have to use that if you don't want to, but all I care is you got to show me that it works. You got to show me that convolution is done. I included the test case in the starter file is the same x of n and h of n from that example we did in class, the one we did in class by hand. That way we all kind of know what the output, that way you know what the output should look like. So yeah, so if you're not using that, you got to show me that it works properly. So let's see, can you give us more attempts on Blackboard? No, turn in the. I'm not gonna. If you screwed up your name of the project, it's not gonna be that big a deal this time. Just get it right in the future. But no, get your stuff right and turn it in one time, one attempt only. Would I prefer AXV line or stem on project 1? It doesn't matter as long as it looks good. As long as we have 2 signals and their convolution plotted, then that's all good. Yep. Yeah, the important thing is that you implement the convolution line by line in code. Any other questions, comments, concerns? Okay, in that case, enjoy your long weekend. Be safe, don't do anything stupid, don't get sick. And I'll see you guys on Wednesday. Thank you.
Have a nice day.
You too. How many test benches do you need, Jason? As many as you need in order to get it done.